you very much. I know this is a graveyard hour where everybody is sleepy, especially with all this COVID-19 hanging around our neck. I know that I would rather be having an evening walk rather than sitting here in this online class. But anyway, that's just how the way it is. You just have to go through with that. Okay, so with that aside, we are still talking about this partial fraction thing. How can we perform the decomposition using partial fraction? There is a special case here that we have not talked about. Again, in control engineering, we are not really interested in special cases. Probably mathematician would be interested in, but just to cover the basic here, seldom that you are going to be asked question where there is repeated roots. But just for the sake of completeness, let's say for some reason, if you encounter a transfer function with repeated root where you have a double root, for example, s squared instead of just s, and for example, s plus 2, the whole thing square, then you're going to have a repeated root. So in that case, the composition of partial fraction, you have to take care of both roots. See, you cannot decompose here a1 divided by s plus 2, a2 divided by s, and then a3 divided by another s. Those just not independent of each other. It is just now you have 2a2 divided by s, then you only get 2 coefficients. But when you have 3 factors in the denominator, you should be able to find all these 3 coefficients, a1, a2, and a3. So the correct decomposition of partial fraction for s squared here is a2 over s, and then another term, a3 over s squared. Similarly, if you have double roots in the s plus 2 here, let's say s plus 2 squared, and then you have a1 divided by s plus 2, and then there's another coefficient divided by s plus 2 squared. So that is how you decompose when you have a repeated root. See, mathematician loves all that. So they talk about special cases as if their life depends on it. But again, you find a1, a2, a3 the same way you find a1, the coefficient from previous example. So you expand the term, compare the coefficient, and solve 3 equations, 3 unknown. Then you're going to have this a1, a2, and a3. But the last time we were talking about an easier way. How can we find this coefficient a1, a2, and 3 the easier way? See, it is called the residue method. Sometimes I call it the remainder. Some people call it the remainder. So I call it the residue method. So this is a remainder theorem. A partial fraction can be solved using remainder theorem. See, the remainder theorem says that if you have the transfer function in the form of quotient of numerator represented by n of s divided by the denominator of s that can be decomposed into partial fraction, then the coefficient of the partial fraction can be easily evaluated by this remainder theorem. Sometimes this is also called the cover-up method. So you take the original transfer function, which is numerator and denominator, and multiply by the factor that you want to find the coefficient of. Let's say if you want to find the coefficient ai, so you just multiply by by the factor I, and then you can cover up. This can be cancelled out with the denominator. You evaluate that using the roots of that factor. I know you don't understand any of what I have just said, right? Do you understand any of what I just said? Or it sounds like I'm talking in German? I think this COVID-19 is really getting to me. My head is not thinking straight. It's like something is bothering me. But never mind. Okay. All right. Okay. Let us try to clarify that. Okay. Let us try to clarify that. And look at this example. See, solve. So given this equation, this is what I like about being mathematician. See, I wish sometime I am a mathematician. See how short their question is. All they have to say, solve. See, and then you have to think about it. What do they really mean? So solving here meaning that you want to get y as a function of t. See, engineering problem normally have a long description and represent a real physical system. But when a mathematician talk, it just say solve, and then they go away and expect us to understand that. By the way, forget about it. I'm rambling too much today. I don't know what's going in my head right now. Never mind. All right. So the idea here is to get y as a function of t with all this initial condition. So the step is still the same. We take the Laplace transform of this equation, and then we perform the partial fraction, and then we are going to determine the value of the coefficient using this remainder theorem. After that, we take the inverse Laplace of that. All right, but I have the solution ready for you. Okay, the solution is ready. Okay, so this is the remainder theorem. Okay, now let's solve that equation. Okay, so now you need to take the Laplace transform of this differential equation. This is the initial condition. If you take the Laplace transform of the second derivative, so second derivative, you need to go back to the table of second derivative. Where is it? Where's the table? All right, there's a table. So this is the second derivative. The Laplace transform of a second derivative is s squared multiplied by y of s minus y minus s y of 0. So this is the initial condition, the value of y at time t equals 0 minus the value of the derivative of y at time equals 0. So you need to, since the initial conditions are not 0, so we need to consider all the term. And the Laplace transform of the first derivative is s y of s minus y of 0. Distinguish between capital Y and the small y. Small y represent the time domain, the value of y at time equals 0. Okay, so now you take the Laplace transform of the first derivative, s squared multiplied by y of s minus s y of 0. Y of 0 is 2, is given here. The initial condition is y of 0 minus y dot, the second derivative, the derivative of y of 0, so minus 1. So this term here comes from the initial condition. Now take the Laplace transform of the first derivative. So 5 is just a coefficient, so you have 5 there. And then the Laplace transform of the first derivative is just s y of s minus y of 0. Y of 0 here is the value of y when time equal to 0, which is the initial condition, which is 2 here. Okay, and then the Laplace transform of the variable, just y of s. 12 is just a constant, and then Laplace transform of e to the power of t, and you need to go back to the table. Okay, so you go find e raised to the power of t there. So this is exponent e raised to the power of negative alpha t 1 over s plus alpha. So now you can take the Laplace transform of exponent here. So since this is a plus, this minus there. So this is the Laplace transform of the of our equation. And then you need to solve for y of s, or expand everything and bring the coefficient to the right hand side. And then of course this is just basic algebra. And then you can now solve for y of s. This now become an equation in terms of y of s, where you can solve for y of s. And if you are careful enough, then of course, so this is this, when you solve for y of s, then you get this transfer function. All right, so I'm not going to show you how I get from solving this. This is just basic algebra. I'm expecting everybody can come up with the solution. What we want to talk today is how can we decompose this this expression into partial fraction. That's what we want to discuss today. Not about solving an algebraic equation. No, that is elementary. Okay. So now we have 3 factor in the denominator. When you have 3 factor, which is s minus 1, s plus 2, s plus 3, you're going to have to find 3 coefficients. So when you decompose that into partial fraction, you have a1 divided by the first factor, a2 divided by the second factor, and a3 divided by the third factor. a1, a2, and a3, we are going to determine a1, a2, a3 using the remainder theorem. The remainder theorem. This. So a1, so this is ai. So a1 is going to be numerator divided by denominator, which is the original quotient, multiplied by s minus s1. So this is the first factor. And then you evaluate the whole expression at the roots of the first factor. In this case, si. So let us do that. Okay. So a1 is equal to the original expression. This is original expression multiplied by the first factor, which is s minus 1. Evaluate that at the roots of the first factor. So the root here is equal to 1. The roots is simply the value of s that will make the denominator equal 0. So when s is equal to 1, so the whole thing goes to 0. So you evaluate this expression when s is equal to 1. See, now you see that this s minus 1 in the numerator, s minus 1 in the denominator, you can actually cross that out. So these 2 factors can be crossed out. Sometimes this is called the cover-up method. Cover-up meaning that you cover this s minus 1. Because 1 is in the numerator, 1 is in the denominator. Not cover-up, the meaning of cover-up for a crime or something like that. No, there's a different cover-up. So this is just crossing this factor out. Now you just substitute s is equal to 1 in the numerator. So 1 squared is 1, 9 multiplied by 1 is 9. So 2 plus 9 plus 1 is 12. And then you substitute 1 in the numerator. S minus 1 has been cancelled out. So this is 1 plus 2 is 3. 1 plus 3 is 4. 3 multiplied by 4 is 12. And then you get 12 in the denominator. 12 divided by 12 is equal to 1. So that's your value of a1. See, how easy is that? You can quickly determine the coefficient of partial fraction, especially in your test. I promise you, this type of question is going to come up in your test. I'm willing to bet money on that. Even though I'm not the one, who's going to set up the question. I promise you that this type of question is going to come up in your test. And knowing how to evaluate the coefficient of this partial fraction using remainder theorem is going to save you a lot of time. All right, so A2 is the numerator divided by the denominator, the original expression. You multiply that with the second factor, which is s plus 2, and then you can now cancel out s plus 2. One of them is in the numerator, one s plus is in the numerator. You can cover this up. And then you evaluate at s equal minus 2, which is the root of the second factor. Root is the value of s that will make the numerator equal 0. So in this case, if s is equal to negative 2 plus 2 is 0. So you evaluate at the root. Now you just substitute 2, and then in the numerator, substitute 2 in the denominator, you get negative 9. Wait a minute, where's the negative sign goes? All right, okay, there's something not right here. Let's evaluate this together. This is 2 squared is 4. 4 multiplied by 2 is 8. 8 minus 9. No, 8 minus 18 is minus 8. Wait a minute, what's going on here? This is 4, this is 8. So this is minus 18. Minus 18 plus 8 is 10, is minus 10. Minus 10 plus 1 is minus 9. So the numerator is correct. And the denominator, so we cover that up. Negative 2, negative 1 is negative 3. Negative 2 plus 3 is 1. So it is negative 3. So it's negative 3. Okay, so make a correction there. So this is negative 9 divided by negative 3. So you get 3. So the answer is correct. So there's a missing a negative sign there. You know that I did this on purpose. See? I omit negative 3 on purpose so that we can have a discussion. So how about that? It's pretty quick cover up, right? No. This is my honest mistake. Don't worry. And you repeat that for A3, and then you get negative 2. With that, you can now easily perform the inverse Laplace transform to get this solution. So now that you have a quick and easier way to determine the coefficient of partial fraction. Do you have any question now? Okay. Is it only applicable for s equal minus 1? How about the denominator has s to the power of 2? All right. This guy is making my life difficult. See, the question is, what if the power of 2? This guy is making my life difficult. Okay, let's say now, in the numerator, you have a quadratic equation. I actually anticipate that kind of question. Now you have some. Okay, just when you think that you have everything, let's imagine now in the denominator, you have a quadratic equation here, s to the power of 2. See, the Muhammad Shafiq there. I know a guy named Shafiq is always brilliant. I know that. No, I'm just kidding. Some of them is dumb as well. See, what happens if you have a quadratic equation? So you're going to have two types of solution. If the roots are distinct, are real and distinct, you can factor this out. But sometimes the roots are complex. When the roots are complex, you cannot factor this quadratic equation out. So in that case, the solution for a quadratic equation here, of course, you need a more complete Laplace transformation table. If you have your engineering mathematics book, and if you go to a Laplace transformation table, you can find this term in the Laplace transformation table when the roots are complex. So this is the solution. we will use this solution when we trying to solve a second order equation. Right now, you just accept this. So if this is the Laplace domain f of s, when you take the inverse Laplace of that, so you get this is f of t, 1 minus whatever. Zeta here is known as the damping ratio. Omega n, the name omega n here is known as the natural frequency. We will come back to this when we talk about the solution of the second order equation. Right now, don't make my life difficult. Don't ask too many questions about this second order. I'm not a mathematician. I'm just using the Laplace table to perform this inverse Laplace transformation. All right, by the way, put that aside. Do you have any other question? Okay, so that's it. Okay, we are done. We are done. All right, so we can now go to my next. Where were we? Okay, so we are done with this remainder theorem. See, this is a second order. In this case, you cannot factor this out because the roots are complex. So I've given you the solution for that. We'll come back to this when we discuss a second order equation. All right. So knowing how to solve differential equation, how to solve, how to get the response of a transfer function. Now we are going to talk about the time response of first order system. So from now on, we don't care whether the transfer function represent translational mechanical system, rotational mechanical system, a fluid level system, or whatever system, as long as it is first order, then the solution is the same. So now we want to classify the control system in terms of the order. The first order simply stated that the highest order of S in the numerator is 1, so that is the first order. If the highest power of S in the numerator is 2, and then we say that we have a second order. A more appropriate classification of control system is defined here. So normally the transfer function is in the form of ratio of polynomials. See, sometimes the ratio in terms of factor that we have discussed about. But when you expand the factor in the numerator and in the denominator, you are going to get a polynomial, one in the numerator, one in the denominator. So the order of the system is known as the highest power of S in the numerator. That is the order. All right. So when we write the transfer function in terms, so the classification of the control system is made using the open loop transfer function. I forget about that. So this is a control system. This is a closed loop system. So the open loop transfer function is just the loop gain, which is k multiplied by gh of s, not the whole transfer function that relates input to the output. See, the classification is made based on the open loop transfer function, which is defined as k multiplied by k multiplied by gh. In this case, h is equal to 1. So the loop gain of a control system is known as the open loop transfer function. So the classification of system is made based on the open loop transfer function. So how do we classify a control system? So once you have put the open loop transfer function in terms of polynomial like this, and then the order is the highest power of S in the denominator. The rank which is not that important. So what is important is the class and the order. So the class and the order is going to distinguish how the system is going to respond. So the rank is just the order of S in the numerator minus the highest power of S in the rank is just the highest power of S in the denominator minus the highest power of S in the numerator, and the class is just L. L is this S raised to the power of an integer there. So L is known as the class. Again, I'm going to explain this using example, which is much easier. Explaining this using example. Okay, let's see now. This is our open loop transfer function ABC here. So, example 1, determine the order. The rank and the class. Order is the highest power of S in the numerator. Here it is 4. So this is system. The order of the system is 4th order. The rank is 4 minus 1. The highest power of S in. Okay. Wait a minute. I have this written in my notes. Okay. Oops. Whoopsie. Okay. Where is it? All right, there you go. Okay, I have this written in my notes. Okay, all right. Okay, so the order is the highest power of S in the numerator, which is 4th. So this is the 4th order system. The rank is just the highest power of S in the numerator minus the highest power of S in the the highest power of S in the denominator minus the highest power of S in the numerator, which is 4 minus 1, so you get 3. And the type here is S raised to the power of 1. It's outside this polynomial. The power of S outside of the polynomial, we say that is the class. Okay, so let's go to B. So this is 5th order. The highest power of S in the denominator is 5. The rank is also 5 because there is no S in the numerator, S raised to the power of 0. So 5 minus 0, you get 5. And the class of the system is 3. See the single S raised to the power of 3. So that is your class 3. And the last transfer function here. The order is 3rd order. The highest power of S in the numerator is 3. Rank is 1, which is 3 minus 2. 2 is the highest power of S in the numerator. And then it is a class or type 0. There is no single, you cannot factor out S out of this polynomial. Therefore, your type is type 0. So from now on, we don't really care whether the system is translational mechanical system, rotational mechanical system, as long as we are going to solve it according to the order of the system. So today we are going to talk about the time response of the 1st order. What does the word 1st order comes to your mind? When you hear the word 1st order, anybody? I was thinking about Star Wars movie, right? The 1st order. Okay, forget about it. First, okay, forget about it. No. Okay. Never mind. I'm just rambling. Okay, so now we are going to solve the time response of a first order. So these are some example of first order system. Okay, a translational mechanical system without mass, so that's going to be first order as well. Okay, let's go to my notes. I think I have that covered. Okay, these are three examples of first order system. Okay, so this is translational mechanical system. When there's no mass, then you don't have the second derivative. So the transfer function between input and output xo divided by input xi is just that. So this is a first order system. The highest power of s in the denominator is 1. Here is the oven. So the temperature divided by the heat in is just that. So the highest power of s in the numerator is 1. And then also a field control. Field control DC motor can be approximated with the first order system as well. So the torque produced by field control motor with respect to the voltage that you supply to the field winding is going to be first order as well. So we don't really care what physical system the transfer function represent, as long as it is first order, then the characteristic of the response is going to be the same. Okay, so how can we solve this first order system? So in general, this is the transfer function of first order. K divided by 1 plus Ts. K is known as the gain and T is known as the time constant. Okay, so I think this is appropriate time for us to take a break. I'm not going to go through the derivation of all that. Okay, so let us take a break here and come back at 4:45, and then we will discuss the time response of a first order system. How does the characteristic of time response of a first order system is going to look like? So I'm going to take a break here. So let's come back at 4:45 and we will continue from there. All right, so see you at 4:45.